So we're going to talk about this distribution called the t-distribution. And the t-distribution is going to be used now because in every problem we've done so far, we've pulled our standard deviation from a sample. And the way we build this is we look at it as there's two types of standard deviations. There's the population standard deviation. And in the population, remember, you have to know everything, or every individual has to be able to give you information from it. Generally speaking, we don't have this luxury available to us. And we have to look at the sample. So our information generally comes from the sample. And in a confidence interval, everything comes from the sample. Because recall that in a confidence interval, you're using the information you get from the sample to generalize plausible values for the population. So because of that, here's what's happening now. We are now looking at, it says, it is rare that we know the actual population standard deviation because we don't know everything in the population. We're actually gathering from samples. And because of that, we have to actually use S of X, the sample standard deviation, to make our decisions now. And what's happening now is we have two distributions that we've talked about. We talked about the normal distribution. And in normal distribution, remember this, the normal curve looks something like this. And in a normal curve, the mean sits here. Here is mu. And as you get closer and closer to the tails, notice that the area of the tails over here and the areas of the tails over here are very small, right? Well, when we pull from samples, generally speaking, our samples are going to be smaller than the population. And because of that, the amount of error that we're going to allow ourselves in this sample right here in the normal curve, the amount of error you have in these tails is going to be minimum because you know everything about the population. Well, if you have a sample, samples don't give you everything about the population. They're parts of it. So you need more error. And so we do that by creating a curve that looks something like the normal curve, except now we're going to allow this curve to have more area out here in the tails, which means when you have more areas in the tail, that means that you have more extreme values. And this is going to develop what we call the t-distribution. And the t-distribution is still a unimodal and symmetric distribution. So it's bell-shaped, just like the normal curve. It's asymptotic, just like the normal curve, which means it wants to ride that x-axis. But the tails are fatter, and it's more robust, what we say. Robust meaning that it allows for more error than the tails, which means the normal curve says that, this first curve, the black curve, says that very extreme values are going to happen very few of the time. The t-distribution allows for more extreme values, and that's because you're pulling from the sample. So you can think of it as like if you flip a coin, again. If you flip a coin 10 times versus if you flip it 100 times, would you be surprised if you got 3 heads out of 10 flips or 3 heads out of 100 flips? Well, you'd be more surprised if you got 3 heads out of 100 flips because the chances of that rare thing happening is very slim. And that's because you're getting more information about the population. In 10 flips, getting 3 heads is not impossible. It's not impossible because you have a very small sample. So what this is saying is that these sample sizes, when they're small, you can have more extreme values. And this T curve is based off of its sample size. And every sample size every T curve is going to be defined. It's going to have a mean and a standard deviation, but it's going to be defined now by these things that we call degrees of freedom. And a degree of freedom is based off of the sample size. And so the degrees of freedom are equal to n minus 1. And remember, this n stands for the sample size. So the n stands for the sample size. And here's what's going to happen. You can think of a degree of freedom as if, say you had a classroom or a movie theater with 30 seats in the movie theater. As a person walks in, how many different ways can they sit inside those 30 seats? Well, there's 30 different ways they can sit. As the next person walks in, how many ways can they sit? 29. And then so forth, 28, 27, all the way down to the very last person that walks into that movie theater. How many ways can they sit? Exactly one way. So what's happening here is our data is construed in such a way that when you look at the data, certain things are already set for us and only certain things can vary. In this case, we have what's called 1 degree of freedom, which is why you're doing n minus 1. So long story short, it's just the way that the data can vary. But just know that here's what's going to happen. Here's the most important thing. As the degrees of freedom increase, the t-distribution resembles the normal distribution or the z-curve. And that's because, think about it like this. T comes from samples, smaller samples. Z is a populational value. It's a population value. It comes from the population. The population is big and it has more values in it. So just like the t-curve or just like the z-curve, if we get more and more values about the population, what happens to this curve? Well, more and more values means that the samples are becoming closer and closer. The larger the sample size is, the more and more like the population starts to look. And in theory, if we could take all the values in the sample, all the values put in the sample, we'd get the population. So as the T curve, as you increase your degrees of freedom, or as you increase your sample size, which also increases your degrees of freedom, because the degrees of freedom are n minus one. As those things are increasing, this curve is getting closer and closer to the normal curve. And we're going to find these things called T critical values. And again, just like Z critical values, T critical values, remember this curve is based off of a normal distribution, just fat or tails. And so now what you're going to have is, sitting inside of here maybe 95%, right? This is the positive T star, this is the negative T star. And T star, something different about it, is defined by the degrees of freedom. So we're going to use a new function in our calculator. And that function is going to be called the inverse norm function. The inverse T function. If you have a TI-83, you won't see this function. If you have a TI-84, you will see inverse T. So here's some examples. We're going to find critical values in the T distribution. And the T distribution works just like the Z distribution. Look at the following. Find the following critical values for A, 90%. But this time you have to be given a sample size in order to find degrees of freedom. Or you can be given degrees of freedom and know what the sample size is. So here 90% means that you're going to draw a curve. On the inside of this curve is 90%. Which places how much on the outside? Well, we have 5% to both sides, right? So normally we would do inverse norm 0.95. We add the 5 to the 90 to get 0.95. This time we're going to do the exact same thing, so we're going to use the inverse T function. Inverse T, 0.95. And inverse T wants an area, which is at 0.95, and it also wants degrees of freedom. So if n is equal to 10, your degrees of freedom are 9. So you're going to do inverse T, 0.95, 9. Then we use a calculator to calculate that. We go second, and remember it's in bars, and you should see inverse T sitting in there. 0.95, comma, 9. You get a T of 1.833. How does that compare to a Z at 0.95? Well, the Z of 90%, your Z star at 90% is equal to 1.645. Notice that this value, this T value right here, is bigger than the Z value. That's because it's allowing for more air in the tail. That's what it's doing. It wants to give you more air in the tail, and the Z will always be smaller than T. So inverse T, 0.99. So you draw a curve. And on the outside you have, on the inside you have 99%. The outside is 0.05 now to the inside here. And 0.05 on the other side, because it's 1% on the outside. Divide that by T, you get 0.05. So in our calculator, we're going to type in inverse T. This time it's 0.995. And your degrees of freedom for 30, you always do n minus 1. So 30 minus 1 is 29. So we go second bars again. Inverse T, 0.995, comma, 29. And I get an inverse T of, or I get a T star at, we subscript it like this, T star at 29 degrees of freedom. So when you write your answer, you write it as T star, the critical value, at the degrees of freedom, which is equal to 2.756. If we were to do Z star for this curve at 99%, we would get a Z star of 2.576. So notice again, your Z star is considerably smaller than your T star. And again, that's because T star is allowing for more error. So look at the next example. It says first find Z star at 95%. We know to find Z star at 95%, we would draw our curve. %. So we want 95% on the inside of this curve, which puts 2.5 on both sides of the curve. So this will be inverse norm 0.975. And that means that your Z star is equal to 1.96 for 95%. So look what happens here. I want to find all of these T stars now at 95%, but I'm changing the sample sizes on each of them. And notice that the sample size is increasing for each of these Z stars, for these T stars. So this one would be just inverse T. And it's the same process as a Z, 0.975. But you're going to find degrees of freedom. Degrees of freedom for 20 would be 19. If we calculate that, we get this right here, your T star at 19 degrees is equal to 2.093. Here, inverse T, 0.975 again, except this time your degrees of freedom are 99. So inverse T, 0.975 comma 99, and you get your T star at 99 degrees of freedom is 1.984. What happened to the T star when it was 20 degrees? Right here, when we had, 19 degrees of freedom and a sample size of 20, and then we had 99 degrees of freedom, sample size of 100. What happened to your T star? Notice it got smaller. Why is it getting smaller? Let's look at 1,000. So again, we're going to do inverse T. This time your degrees of freedom are 999. So 0.975, 999. And I get, well, here your T star at 999 degrees is 1.962. What's happening to T star as these degrees of freedom or this sample size is increasing? Well, remember this, when we first started, Z star was 1.96. Look at where it is at 1,000. It's going to 1.962. It wants to get closer and closer to 1.96. It's going to get as close as possible. So as the sample size increases, what's happening to T star? It's becoming Z star.